my sincere pleasure to introduce our next speakers. Both are engineering students with a civil engineering emphasis, and they are going to talk about a hydraulic and hydrologic analysis that was used by the next team to do structural design. On the left here we have Aaron Hunter, and on the right, Mike Wilson.
Good afternoon. Like Dr. Hill said, my name is Brian Wilson, and this is Aaron Roner, and our project is the hydrologic and hydraulic analysis of Flat Creek. Today we'll be talking about our project scope, site overview, hydrologic analysis, hydraulic model, design alternatives, future work, recommendations, and our cost report. So the scope of our project was to design a bridge to access a private property that will house a community of family farms. And the requirement that we need to meet is 0.14 feet of backwater, which was provided by the Indiana Department of Natural Resources. And the motivation for our design is it must be cost efficient. So what is backwater? If we have flow going from left to right, and we add a pier, the original water surface elevation is the dotted line shown there, and the water surface elevation after the pier is added is the darker line. The delta Y is the backwater, and it occurs immediately upstream of the bridge. So I'm going to hand it over to Aaron, and he's going to talk about the site overview.
Thanks, Brian. This is a site overview of our project. The yellow thumbtack is the approximate location of our site. It is just northeast of Candleburg, Indiana. Candleburg is located directly east of Washington, Montgomery area in Indiana, so you have an idea where this is at. So we'll get a zoomed in look at our site. Highlighted here is Flat Creek, and this red area here is the client's property that they are actually wanting to gain access to. This is the existing path that they now use to cross the creek to get access to this property. And this is the approximate bridge location. So I'll go through a couple pictures here of this existing path. So this picture here is the existing path that I spoke of earlier that the client currently uses to gain access to the property. And this is another picture of that existing path. As you can tell, it's not really a reliable path for the client to use to access the property. And if they're looking to build homes on that property, they would need a more reliable structure to cross the creek. So that is the purpose for a bridge. And this here is a picture of the creek channel. If you look in the middle of the creek, there are some like sandy islands. That is due to the scour problem in the channel. Later on in the presentation, we'll give you an idea of the scour problems and how we plan to fix the scour. So this is another picture of the creek itself. This picture is actually taken at the approximate bridge location, and the approximate bridge location, as depicted in this picture, does have scour problems, and it's actually more severe at the bridge location than where the existing path is now. This is the floodplain of our site, or of the bridge location. That bridge, if you look over on the that picture there, the floodplain, you can tell, is basically all agriculture all around the bridge, or all around the creek itself. And then on top of that hill in the distance is actually where the location of the client's property is. And so this is standing on top of that hill where the client's property is at, looking toward the bridge. I'm going to pass this over to Brian, and he's going to give you the hydrologic analysis of the bridge.
Okay, so before we could begin the design of our bridge, we needed to determine the amount of flow flowing through the creek. So we needed to confirm or deny the 100-year discharge provided by the Indiana Department of Natural Resources. And one of our first steps at doing this was looking at the United States Geological Survey's online stream stats program, which is a program that uses regression equations that are based off of streams that are being measured and topographic data. And we also looked at the NRCS unit hydrograph method, and a HEC HMS model was developed for that. So here are the results of each of those. The 100-year discharge, We used the 1950 CFS for our 100-year discharge to design our structure. So to design the structure, we used HECRAS, which is a river analysis system developed by the Army Corps of Engineers, and it looks at water surface elevations for streams, rivers, creeks, trenches, whatever that water is flowing in. So two things need to be modeled in HECRAS. It's the flow, which was determined via the hydrologic analysis and the topographic data. So, like I said, the 100-year discharge from the hydrologic analysis. Here's the watershed that was developed from StreamStats. A watershed is any water that lands in the shaded area will discharge to a single point, which is highlighted there, where Aaron is pointing the arrow. And then also, here is the land use of the watershed. It's primarily agricultural, and it's soil group C. I'm going to hand this back over to Aaron, and he's going to talk about the topographic information.
All right, so the next step in the cross-section is creating the topographic map. So we received some survey points, and then we created a surface in Civil 3D. Civil 3D is a design program that you can create different topographic maps. You can even do site grading and drainage. So creating that surface gave us those red lines depicted in that picture. That is a topo map. And then the next step was to create, or to draw cross-section lines along the creek bed. So we took cross-section lines every 100 feet along the center line of the creek bed, and then imported that file into HECRAS, which Brian referred to earlier. That file was imported as a geometry file, and then it created this cross-section. This is a sample cross-section of in HECRAS. If we take a look in here, you zoom in, you can tell that the bridge or the creek averages around 40 feet wide and approximately 10 feet deep. So the cross sections then need some information to input into HECRAS, and that is the reach lengths and the Manning's roughness coefficient. Reach lengths are essentially just the distance from cross section to cross section of each overbank and the channel itself. It's the distance in between those two. The next is the Manning's roughness coefficient. Here is the equation that we determined to find the Manning's roughness coefficient. It is the Cowan's equation. Cowan's equation is basically just some summations of coefficients that take into the factor of the vegetation, any obstruction that's in the stream, and any irregularity in the stream, and then multiplies it by a Manning's factor. So this is our floodplain. Our floodplain had an N value of 0.036 and a channel Manning's roughness coefficient of 0.038. This is uncommon. Most creeks actually have a smoother Manning's roughness coefficient in the creek rather than in the floodplain. But looking from the earlier pictures, you saw all of the severity of the scour from all the islands actually in the channel itself. So that is the reason why that we have a higher Manning's number in the channel rather than the floodplain. I'm going to hand this over to Brian, and he will talk about running the model.
So after the existing conditions have been modeled, we need to make an assumption on a boundary condition. We use normal depth, where the water is typically going to be at during the 100-year discharge. And for that, we have to assume that the energy grade line is approximately equal to the slope of our channel. And here is the water surface elevation, which is on the y-axis, and the reach length is on the x-axis. So after we have the base model completed, we needed to figure out where the bridge location was. It was approximately at station 540, and we were able to obtain that information using AutoCAD Civil 3D. We also needed to know where our bounding cross-sections were and our ineffective flow areas, which we'll talk about those in detail in the next couple of slides. So here we have water contracting through a bridge and expanding back out. The water has to contract down to go through the opening, and then it expands. Due to this, the velocity in the shaded regions is approximately 0. These are known as ineffective flow areas. Here, we have contraction and expansion again. For our design, we use an expansion ratio of 2:1 and a contraction ratio of 1:1. These are typical values. The ineffective flow areas are again shaded in red, and the bounding cross sections are 1, 2, 3, and 4. 4 being where contraction starts, 2 and 3 immediately up and downstream of the bridge, and 1 is where expansion is fully complete. If we look at our reach length here, you can see that we have 1, 2, 3, and 4, but we also have 2 cross sections for geometry. This is due to irregularity of our channel. So after we have the base model and the bounding and ineffective flow areas, we were able to design a bridge. We were able to design a bridge that spans 250 feet and 62.5 feet from pier to pier. And here is the water surface profile after the bridge has been added. The base model water surface elevation is there in blue, and the line above it is with the addition of the bridge. We have 0.12 feet of backwater immediately upstream of the bridge, which meets the IDNR requirement. If we were able to allow the backwater to extend to the furthest upstream cross-section point, we were able to span a distance of 185 feet and 62 feet from pier to pier, which this is a shorter bridge, which will save the client some money. And there is depicted the backwater of 0.14 feet at the furthest upstream cross-section. I'll hand this back over to Aaron, and he's going to talk about a design alternative known as a floodable structure.
Yeah, so to knock the cost down of the bridge, we looked at a floodable structure. A floodable structure is just a structure that allows water to actually overtop the bridge. They can either be precast structures, or they can be cast in place structures. Shown on this slide here, on the left-hand corner is a series of precast box culverts, and the other picture is a cast in place structure. So for our structural design, we came up with a reinforced concrete deck with 2 compacted fill abutments that were actually outside the channel, and 2 precast box culverts that were located in the floodplain. We use these as relief culverts. We came up with a span of 8 feet, a rise of 1.5 feet, and approximately 20 feet long. This is a zoomed in picture of our model in headcrest here. Highlight the roadway and deck of our floatable structure, and it had a span of 38 feet. With the compacted fill, which is highlighted there, that is, as you see, is actually outside of the channel. And those are the relief culverts. So this is the water surface profile of our creek. This is the entire reach length of the creek, approximately 1,100 feet. If we zoom in here, you can see yet again the shaded in area is the original flow length or flow height of the creek before the structure was included, and the top line is is after the structure was implemented into the creek, which we had a backwater of 0.42 feet, which is significantly higher than the INDR standard. So this bridge would not be accepted, and we tried multiple openings to get a floodable structure to work, and we could not get one to work. We feel that it is due to the to such a large flow going in such a small creek. And you can see here we had approximately 1 foot overtopping the roadway. So getting back to the bridge scour that we were talking about earlier when we were looking at the pictures. So we used headcrest again to analyze the bridge scour. There are 2 types of bridge scour. There's clear water and live scour. Clear water is any scour or sediment in motion that is actually around the structure itself. For example, it would be around the pier, around the abutments, or where the structure is actually located in the stream. Where live scour is sediment movement along the entire length of the stream, not just the structure. So this slide here is the results that we got from our headcrest bridge scour model. If you look on the top right-hand side, that is our velocity profile. And if you look on the channel scour, the top left table, you see that we have a scour depth of 0 for the left-hand side. That is due to the critical velocity of the scour actually being greater than what the velocity was in that floodplain. And then if you look, we have the highest, deepest depth of scour occurred in the channel, which is the largest difference between the critical velocity and the velocity of the profile itself. And then we had live scour along the entire length of the bed, which you can see from the multiple areas of scour. And then we had clear around on each embankment, which would be due to the contraction of the bridge. We had an average pier scour depth of 3.72 feet per pier. And then we had a left abutment of 8.14 feet and 7.17 feet scour. So to protect from bridge scour, we decided to come up with, choose riprap as our scour protection. This is a typical scour protection using riprap picture here. And we decided to use a D50 of 6.5 inches. D50 is simply that 50% of the rock is actually smaller than 6.5 inches, and 50% of the rock is actually larger than 6.5 inches by weight. So this table here is from the AASHTO aggregate size appendix. And for a revetment, it has 6 inches, a 6-inch D50, or a 6-inch size opening for 20 to 40%. So we chose slightly over at 6 inches at 6.5 inches to obtain our D50 size. For the area of our scour, we had a 1.5 foot perimeter extension around each pier with 2 feet deep around each pier. And the abutments, we did 2.5 feet wide, extended from the perimeter of each abutment and 2 feet deep. And if you look on that back on the table of the revetment slide, it actually has the minimum depth of 18 inches, but we made it 2 feet due to the significant scour depth. I'm going to hand this back over to Brian, and he will go over the design recommendations.
Okay, for this project, we recommend the client use the traditional structure. It's going to meet the backwire requirement, and it's also going to be accessible during the 100-year flood. And we also suggest that the client purchase floodway easements, which is going to allow the backwire to extend further upstream. This is going to allow the client to build a shorter bridge and really save some money. And for our theoretical cost of this project, this phase of the project, we just have our faculty advisor time at $100 an hour, approximately 30 hours, and our student time at $15 an hour at approximately 360 hours, giving a total cost of $8,400. And then the future work for this project is it needs approval from IDNR, structural design, which will be the following presentation, and their grading and site work plan. And we'd like to thank Mrs. Donna Moore, Dr. Jason Hill, Dr. Carrie Hall, Tim Crow and Amanda Adams, and all of the engineering faculty that have helped us the past 4 years, and our friends and family. And at this time, we'd like to open it up to any questions.
Maybe I'm anticipating a question for the next group here. What kind of bridge is this? Is it a footbridge, a bicycle bridge, a car bridge?
Yeah, so they will be covering that in the next presentation, but it will, to preview that, it's going to be a semi. It's a car. The maximum loading will be a semi.
Okay. And is someone designing the roadway to and from this bridge?
I don't think that's encompassed in this project.
You had mentioned that the average depth of the creek was 10 feet, and then the picture you showed looked like a person was driving through it, like it wasn't that deep. Was that 10-foot measurement based on the 100-year flood or something else?
No, are you going back to, these pictures?
Right.
Yeah, this is, where, if you look in the distance here, is where about where the bridge is gonna go in this area. And we measured 10 feet from the bottom of the creek to the top of the bank is what we had is 10 feet. The water depth kind of varies because it goes up and down. But I think at the bridge itself, the water depth is about 2 to 3 feet or so deep. So from the bottom of the channel to the top of the bank was 10 feet.
Other questions?
When you were building the model of the creek, you did a 100-foot resolution. Is that a standard resolution for creating a model, or should you have one smaller, larger?
No, that is the standard, yeah.
If you would want more and more detail, you could do it cut up. You could cut it up into smaller chunks. If you wanted less detail, you could obviously do it in larger chunks. Based on like 100 would give us roughly 10 to 11 cross sections, which we felt like that would give us a good idea of what the creek bed itself would look like.
All right. Any other questions? Let's give them a hand.